Hi everyone, welcome to my talk. Today I'm going to talk about limitations of optimization algorithms on noisy quantum devices. This is joint work with Olga Garcia Patron from Edinburgh, Daniel Stoke-Franse from the University of Copenhagen, from the QMAF Center, and you can find the preprint this work is about on the archive. You see the archive number there, and it has the same title as this talk. So what is the guiding question of this work? So right now we know we are in the NISQ era. So this NISQ stands for Noise Intermediate Scale Quantum Computers. And one of the central questions of the NISQ era is whether noisy quantum computers, the quantum computers we're expected to have in the next couple of years without any sort of error correction, can also be useful for any real world application. And many current proposals, are in the framework of optimization and can be broadly put as trying to find the ground state or find a low energy state of some Hamiltonian H. And this includes different proposals like VQE, the variational quantum eigensolver, QAOA, the quantum approximate optimization algorithm, or adiabatic quantum computation. All of these classes of algorithms roughly try to prepare or find the ground state of a Hamiltonian H without error correction, which is also the setup of this work. But the question is, does the noise actually hinder us from finding good solutions or outperforming classical computers for this task? In particular, let's say if we could scale the number of qubits but not significantly decrease the noise rates, could we actually still do something useful with such computers? And how do we concretely assess the problem with the noise, right? I mean, how we assess how limiting is noise in such systems for real world applications. And in particular, it is very important to go just beyond classical methods or classically simulating the quantum device. So let's say if we had 1,000 qubits with current noise rates, and if we were to implement a circuit of, say, depth 50, it is very unlikely, or at least it's way beyond current capabilities to actually simulate such a circuit classically easily, right? But this doesn't imply, of course, that the output of this circuit is interesting in any sense for a structured optimization problem, right? It could still very well be the case that a classical computer could find states of lower energy. So it is very important to decouple the analysis of, the potential performance of quantum algorithms to actually simulating these noisy quantum devices, because we don't really have a promise that this is the best way to go with. Maybe some other classical strategy performs better given the noise levels, even though we do not have a way of classically simulating that noisy quantum computer. And this is exactly what we do in this work. So our framework is essentially based on analytically bounding the relative entropy, which you should think of as some sort of distance measure between states. And we bound the relative entropy between the output of the circuit and some easy state that the noise is driving your system to. So imagine you have local depolarizing noise. This will drive your system to the maximally mixed state as the circuit depth increases. So in the limit of infinitely many layers of your circuit, the output is just trivial maximally mixed state. But of course, at some point, you would expect that the noise drives your system to a trivial state. And we do this by estimating how long it takes for the state of your system to be not necessarily maximally mixed state, but to perform as well as a Gibbs state. So Gibbs states are just states of the form e to the minus beta h. Recall that h is the Hamiltonian you want to find the ground state of. And for many classes of Hamiltonians H, it is known that for some parameter range of beta, it is actually possible to simulate these Gibbs states in polynomial time classically. So essentially what we do is try to use the noise to see how long it takes or what's the depth, after which we are already performing as well as some classical, as some Gibbs state, which we can simulate classically in polynomial time. So, and thus, after that depth, the quantum computer will not outperform the classical computer significantly. So note that we are not saying that you can efficiently simulate the output of this noisy quantum circuit. We're just saying that you can find a classical strategy which takes polynomial time and system size and performs approximately as well as the quantum device. And then, you know, as I mentioned before, you essentially compare the output to Gibbs state methods. Now let's just exemplify this with one proposition from our paper. So one of the main candidates for near-term quantum computing is finding the ground states of Ising models, because you can, I mean, these are really widely studied, and it is well known that you can encode many the solution to many combinatorial optimization problems to Ising models. And so what does our method say about solving solving the Ising models on noisy quantum devices? It says that essentially after depth 1 over p, where p is your local depolarizing rate, so this is the local noise rate, so you have a quantum system, and after every layer of unitaries you have local depolarizing noise probability p. Then after this many layers over here, you can find a Gibbs state that can be sampled from in polynomial time classically, and this is not some abstract statement. You can actually easily do this on your laptop, say, such that the energy of that Gibbs state is comparable to the energy of that the output of the noisy quantum device. And well, which means that the output energy will be similar, right? So the noisy quantum computer will not significantly outperform the noisy quantum device after this time. So we essentially confirm the intuition that if you have a noisy quantum device without any form of error correction, then you really you can really just go through depths 1 over 2p, and after that Gibbs state methods will actually outperform your noisy quantum device when it comes to optimizing the energy. But maybe you want to compare the performance of the noisy quantum device to some other algorithm which you know performs better than just Gibbs sampling at high temperature. And so it is desirable to have tools to do exactly that, which again just go beyond simulating noisy quantum circuits of large size, right? And we also provide a technique to do this. So this is based on the variational formulation of the relative entropy. And from it, it is possible to derive the following bound. So if, again, phi of rho is the output of some noisy quantum circuit, H is the Hamiltonian we're interested in, right? It says that the following lower bound holds for the energy of this noisy quantum device. So let's try to understand what are the terms of this equation. So this thing over here is clearly the partition function of this model of this H we're trying to minimize. And note that for, as I mentioned before, for many interesting models, it is known that for a small parameter range, like for beta between 0 and some constant, you can actually approximate actually this partition function efficiently. Okay, so for some parameters of values of beta, you can actually evaluate this term over here. And using strong data processing inequalities, which is a method we discuss in more detail in the paper, it is also possible to estimate this term over here, which corresponds to the relative entropy. So if you have an upper bound on this thing for any initial state rho, and you can compute this thing approximately for some values of beta, then note that we're taking a supremum over here, right? So any point over here will give you a lower bound on the energy of the output, right? So this means that you can evaluate this for some values of beta. You can estimate this term over here, which, as I mentioned before, you can do without actually having to simulate the quantum device. So you can efficiently evaluate this bound. And let's say you get a value of 5, okay? So this means that the energy of the output is lower bounded by 5. Then you can just run your method to solve the problem classically. It can be in a heuristic method, it can be anything. It can be just an educated guess. And let's say the output of the classical method gives you an energy of 4. Then you know that this noisy quantum device will be outperformed by this method, no matter which circuit you implement, because this lower bound here tells you that no matter what you do, the energy will always be 5. And it is well known that you can encode the solution to MAXCUT, which is probably one of the most widely studied combinatorial optimization problems, and it is known to be NP complete, into finding the ground state of an Ising Hamiltonian. And there are many known heuristic and also rigorous polynomial time algorithms to approximate the value of MAXCUT. So we could, for instance, compare the performance of these different methods to what we get by evaluating the bound I discussed before for the parameter range of beta, which is for which you can do it efficiently. So the relative entropy density down here essentially counts how many errors you made, like how many expected errors you have per qubit. And you can see that essentially at already 0.4 over p, this red curve is above, for instance, the SDP solver or the heuristic solver. So this means that the output of a quantum device with this relative entropy density, which corresponds to less than 1 expected error per qubit, will already be smaller or higher, sorry, than if you were doing a polynomial time classical optimization method. So we see that even with, so running the bounds and doing some back of the envelope computations, we actually see from our bounds that even with noise rates like 0.01 to 0.005, you would have a depth of between 50 and 250 before you lose any potential advantage. So if you need a linear in system size depth, or you require high connectivity for your to run your algorithm, which means you have to do many layers of swap gates in between, then there's only potential for quantum advantage at very small system sizes. So which constrains the potential of such algorithms to demonstrate a convincing quantum advantage for optimization without any sort of error correction. But we do much more in the paper. I just scratched the surface. As I mentioned before, we also do analyze quantum annealers under noise. We discuss more noise models than just the depolarizing noise I discussed here. I also only discussed the consequences of our bounds for quantum problems, but classical problems, but we also discuss quantum problems. And I feel that there's a lot of potential in this technique, a lot still stuff to be done. So please check out our paper, and thank you for your attention.